Hi everyone, welcome to another interesting class on control systems. In today's class, we are going to talk about root locus. We are going to see how to solve and plot root locus for a slightly difficult numerical. So the g of s into h of s is given in your question, and it is given to be k upon s into s plus 4 into s squared plus 4s plus 20. So this is the question, and from this question what I have to infer is my h of s is equal to 1, right? Or no, that is what it means because it is given as a unity feedback system. So my h of s is 1, and now I need to plot the root locus for this given system, and in order to do so I need to follow through my 5 steps for plotting root locus. So the step 1 is to identify the poles and the zeros of the given system. So I can tell that my numerator doesn't have any s term, so which means by zeros are non-existent for the system, and because there are no s in numerator, and in my denominator I have s to the power 4, which means I have 4 poles because the denominator represents your poles. So now my P1 equal to 0, my P2 equal to minus 4, and my P3 and P4. So I can find the poles which are computed as the roots of that polynomial, and the roots of that polynomial is computed by making that equal to 0, and then I get this s equal to 0, s equal to minus 4, and then for the quadratic roots I'm doing the quadratic factorization, and I get my P3 and P4 to be minus 4 plus 4j and minus 2 minus 4j. Alright, so that is for your this P3, P1, P2, P3 and P4. And now we can find your step 2 is to find the root locus on your real axis. So in order to do that, what are the steps? So I'm going to take which are the poles on my real axis. So I have my P1 equal to 0 and my P2 equal to minus 4. So these two poles are existing on my real axis, and then I'm going to take two test points right between so that there is at least one pole or 0 on the right side of the test point. So my test point 1, I have the total number of poles and zeros to the right side is 1, which is my odd number. So which means that point is included in your test point 1. Good. And then for my test point 2, which is from minus infinity to 4, that takes care of the space between minus infinity to 4. I have even number of poles and zeros. My P1 and P2 become even. I have 2 poles, and that is not a part of the root locus. So the root locus on the real axis exists only between 0 and minus 4. Good. I can say, yeah. So the space after that is not existent. So that is why I have marked that to be x. So I can write these statements here. For my test point 1 to the right side, I have odd number of poles and zeros. So whenever I have an odd count, that means that is part of the root locus on real axis. And when I have even number, as in the second case, that is not part of the root locus. So I'll just write these statements here, and this must be followed through because these are some of the steps where you don't have to do much computation. Okay. So that is my test point 2. Alright, so after step 2, I'll be going to my step 3, which is computing the asymptotes and your centroids. So you're going to find the asymptotes using the asymptote formula, and then you're going to find the centroid, and then you're going to plot these. Okay, so we have been doing. So let me get to that slide. So let me finish off this. All right, so I think that x will be misleading because since I'm using the poles also with that x, so I'm writing in blue. So this is from minus infinity to minus 4. So we have identified the root locus on the real axis. Now let's move on to finding the angle of departure. Sorry, the angle of asymptotes and your centroid. So we have not done that step 3. So step 4 is your angle of departure. So now let us see what are the angle of asymptotes. The formula, we just direct substitution of formula, plus or minus 2 cube plus 1 divided by the number of poles minus number of zeros, and that should come, in this case number of poles is 4, and my number of zeros is 0, so that should come to be 4 minus 0, which is 180 into 2 cube plus 1 divided by 4 minus 0, and that is plus or minus 45 and plus or minus 135. So this is your angle of asymptotes. And then for my centroid, so what about the centroid? The centroid is given by the sum of poles minus sum of zeros divided by the number of poles minus the number of zeros. So I'm just going to sum up all the poles, and then I'm going to take, there's no zeros, right? So this question doesn't have any zeros, so the sum of 0 is 0, and there are no number of zeros also 0. So I will take this, and I'm going to get the answer to be minus 8 by 4, and that's minus 2. So my centroid is at minus 2, and I'll be using these two angles. Mostly for the angle of asymptotes, we stick to the first angle, but when we project it on all four quadrants, maybe you get the other angles also, but it's not, don't get confused with all these angles. We just go with the first angle. Whatever the first angle you're getting for q equal to 0, use that one. And now coming to the angle of departure. So there was this doubt, like, what is the angle of departure and angle of arrival? So we are not seeing a lot of details on root locus, right? On the meaning of root locus, meaning of asymptotes, meaning of centroid, how it relates to your system, because most of the questions are on to finding the parameters. So I'll just tell you, this angle of departure is when you have an imaginary pole. So in this case, you have minus 2 plus or minus 4j. So you have a complex conjugate poles. So that will give you an angle of departure. Suppose what if you had a complex imaginary, right, complex conjugate zeros. So when you have a complex conjugate zeros, and that is called as the angle of arrival. So the formulas are exactly the same. Just when you have pole, it's angle of departure, and similarly it is called as the breakaway point. And when you have zeros, when you have complex conjugate zeros, it is known as the angle of arrival or the break-in points. So that is for the angle of departures and angle of arrival. So let us see how it is. It is now theta 1, theta 2, and theta 3. So how it is computed? It is computed by drawing a projection line between the poles, right? So between the distinct poles without the symmetry. So these yellow lines, yellow dashed lines, represent that distinct projections without the symmetry line. So I'm not duplicating it. When I do the symmetrical lining also, that means when I do the symmetric projection, then I'm duplicating that line. So we don't want to do that. So by doing this, I'm getting the angle of departure to be minus 90. So the next step is to find the crossing point on the imaginary axis, and for that I have to take the characteristic equation and equate that to 0, and then take the imaginary part and the real part, and then find the value of k. So crossing point on the imaginary axis is given by your omega, that is a frequency. So let us see what is the crossing point, because s is equal to j omega. So let's come to that. So let me take the transfer function. So what is the transfer function formula? That for this system, it's going to be g of s divided by 1 plus g of s into h of s. So my g of s is given to me in the question, k divided by s into s plus 4 into s square plus 4s plus 20, and my h of s is 1. So I'll just plug in these values, and then coming to, after simplifying, I'll end up getting my characteristic equation. So my characteristic equation is equal to k into s plus 4 into s square plus 4s plus 20 plus k. Okay, so that is your characteristic equation. Okay, I forgot to write that plus k. So that plus k is there. So if I simplify this, I take the LCM. So my denominator cancels out. So I've written it. So that plus k is there. So this is the characteristic polynomial. And now I have to solve this by putting my s is equal to j omega. And when I do that, I get the value of omega. And that value of omega is my crossing point on the imaginary axis. Alright, so that is your step 5. So you have to do all this step 5. The only step I'm not doing here, again I'm telling you, is the breakaway and break-in point, because that is very tedious. It's something, cannot, if you want to do it on the pen and paper, it takes like a half an hour of your exam time. So we don't want that. So practically what we do is just as leniency to students, we select questions where your breakaway points doesn't exist, right? So we pick questions in that manner so that you don't waste a lot of time computing this. But what I will do here is I am going to show, I'm not going to use the traditional pen and paper method for breakaway point. I'm going to tell you how to plot the breakaway point with all these 5 things. So now I have steps 1 to 5. So I'll go right into the root locus plotting, and then I will tell you how to do the breakaway point, how to compute the breakaway point from the graph. Okay, so that should be almost approximately equal to what you get with your pen and paper computation. So that should not, no, it should be fine. So for those who are very interested in learning this breakaway point, I have taught this in the previous lecture. In my first lecture on control system, I have shown you how to compute the breakaway and break-in point. So that is the pen and paper method of doing it. So for today, I'm going to show how we can do it from the graph. Okay. So since the whole point, the question, the for root locus is going to be for like 12 marks, and each of the step is going to carry 2 marks. Your final plotting is going to have a weightage of 3 marks, right? 3 to maybe 2 to 3 marks. So that is how your 12 to 14 marks split up turns out to be. So the breakaway point carries no, approximately weightage of 2 points. So if you get stuck with that computation, then it is very much it's not very smart to do that. So we will see how to do it on the graph, and if you plot it on the graph and show it on the graph, you will still end up getting most of your marks, or even 2 marks, right? Most of the students we give it. So I'll show you how to do it in your graph. So that's about the breakaway point. And now what I'm gonna do is, for plotting, I'm gonna use the Scilab, because I can use the graph sheet and plot it, but that is what you are supposed to do. So you cannot use the Scilab program to plot this. So I am using a Scilab program, which is an open source software. It is free to use. You can download it, you can install it on your computer and type this small paragraph of code on this left hand side, and you will see this root locus. So this is what you will be seeing when you do this numerical. So s into s plus 4 into s square plus 4s plus 20. When I'm doing that, I'm getting this p1, p2, p3 and p4. All right, so this is your poles. I have 4 poles that is pointed, and they have joined them, and that is my centroid. So you see the centroid right there, minus 2. So I'm just labeling things for you. So asymptote at plus or minus 45 degree, right? So asymptote at plus or minus 45 degree. On the bottom side, it will be plus or minus 135 degree, right? 180 minus 45, doesn't matter. So you can take the centroid and you can draw from the centroid, you have to draw this 45 degree. So that is your asymptote here, shown in gray line. And now what else is there? The angle of departure. Yes, the angle of departure is there, right? So that is the curvature I am seeing from the pole. So that is not shown here. The angle of departure is not shown in this diagram. Okay, you can show that, but let us now label this. This is 135. So okay, so this is a very good indication. Okay, so the angle of departure is minus 90, right? So that is why that vertical line and the horizontal line, that your line joining the poles, that is your angle of departure, because it is minus 90. So now this is the breakaway point, plus or what is that? Yeah, that is the place where my asymptotes join. So if you just draw a 45 degree line with your protractor on the day of the exam from the centroid, you're going to see that your asymptote is going to touch the imaginary axis at plus or minus 2j. And now I'm going to tell you how we can plot this from the breakaway point. From this, so in order to find the breakaway point from this graph, you need to have an asymptote which is not horizontal or perpendicular. So if you have an asymptote which is at 180 degree, or if you have an asymptote at 90 degree, your breakaway point doesn't exist. Good. So you need to have an asymptote which is at a certain angle. So in this case, it works fine because I'm having at plus or minus 45 degree. So I am plotting this plus or minus 45 degrees. So which means if my cross point, so what I'm telling is, if my plus or minus 2j is, it comes greater than your asymptote. So your asymptote is plus or minus 2j. So which means then the breakaway point exists. The breakaway point is a tangent line from the 3j to this point 2j. So I'm gonna show you how the breakaway point can exist. So these are the 4 poles I have. And now I can draw the breakaway point as a tangent. You just draw it very close to your asymptote. Okay. And how close you can bring it is you can no, that is decided by the breakaway point. But we can't show accurately, but bring it as close as possible and allow a certain gap. Okay, so that I allow. Normally what I do is, here the difference is like 1j, so I just project from here. I just draw as close as possible to this asymptote intersection, and I just take this line. That will come to be something like 1.5. So that is what normally I give. So just a freehand drawing and taking the point, right? That is how I'm telling you to do breakaway point, because that is the only step which is too much indirect and too time consuming. So all the other 5 steps, if you do, you get full points. For this is just, I'm telling you, for for some students, I'm just telling this as an example on how to get the breakaway point. Okay. So your graph will look the same, but the breakaway point will be slightly different, and you may lose one. Maybe no mark will be lost for your breakaway point, and your breakaway point is only it is only a part of a difficult question. So when you have an easy question, you like this, in this question you don't have a breakaway point. So if you see, because your asymptote is, the gray line is at 90°, so it is at a perpendicular, so which means you don't have the gray you don't have the breakaway point. So your poles and zeros are plotted, so not much is there, because it's a very easy question. This is an easy level question. So your root locus looks something like this, and then your real axis on the root locus also can be done. So this will be the real axis, root locus on real axis. You do that. Okay, and then that will be the centroid from the line. So now that is your asymptote, and asymptote passes through the centroid. So that point is the centroid, and there is no breakaway point. Okay, so I'm just using this Scilab to show you the root locus of some of the examples, but I strongly suggest that you plot these, you do these steps, you compute it, and you see. And another question, which is a textbook question, is this: s square plus 6s plus 25 divided by s. So here you're having what? You're having a quadratic 0. The numerator is quadratic, which means I have complex conjugate zeros, and that is going to give my angle of arrival. So now I'm going to have angle of arrival and angle of departure, because my zeros z1 and z2 are complex conjugate. So my asymptote is at 180° here, and these are the angle of departure. So what I have here, that is my angle of arrival. Sorry, this is my angle of arrival, because I'm having complex conjugate poles. And again, since my asymptote is 180°, there is no breakaway point, or there is no break-in point. I can just tell the breakaway point doesn't exist, and if you write that, you get two marks. Good. So easy and medium level questions normally don't contain breakaway points, so that you can identify that from the root locus plot. From steps 1 to 5, you should be able to tell whether your breakaway point exists or not, and if it exists, you can try plotting it directly on the root locus. If you don't have time to do the steps, else please refer to the first problem on root locus and see how we compute the breakaway point. Good. You just take dk by ds. You have the characteristic equation, which is plus k equal to 0, and in that you take the differentiate k with respect to s, put it equal to 0, find s, and then put the value of s in that characteristic equation, see if it is positive. And if it is positive, that value of s is your breakaway point. So these are the steps for computing breakaway point. So good. So this is another question. Here your breakaway point exists because your asymptote is at 45°. Right, and you have the poles P1, P2, P3. Then you have your centroid, and that is your breakaway point. And what I can tell is, here if you see, your tangents are not, your asymptotes are not like, x. It's not an x like the difficult question we have seen. That is mainly because there is no pole on this side of the axis. So I'll draw an imaginary pole, and I'll show you where you get this x-shaped asymptotes. So that is when I have an imaginary pole. So okay, breakaway point exists here. So let's see, what if I had a pole here? So let us say I have a pole here. Now it's non-existent. I'm just telling a hypothetical situation. When I have a pole here, then my asymptotes carry towards these sides. If this pole existed, good. So then you have this projection, and your breakaway point will come on where? On that side. So it will be a tangent to. All right. Thank you.